after a while actually in the field research we
How?
changed into XP.
How?
Yeah.
I think we see still the first slide. Did you change to the following slides?
Yes, already go to the second one.
How maybe you have two screens? Maybe there is because we still unfortunately see only the first slide where it says CMOS millimeter wave radar.
Okay, strange. Okay,
Oh,
let
yes.
me reach. Now is that
Yeah,
okay
yeah.
now?
Now we see motivation. Yes.
Let me actually just reshare everything.
Or maybe you can go into presentation mode, as you prefer.
Okay. Is now it's okay?
Mm-hmm. Yeah, yeah, please go ahead.
So from the 60 gigahertz to the 77 actually is a natural trend. In that year actually we want to actually have more bandwidth to increase the resolution. And later on, okay, everyone we move to the MIMO radar. From the MIMO radar, actually, we want to use a virtual array to increase angular resolution. Of course, inside that the MIMO radar or inside the 60 or 77 gigahertz radar, a very critical part is fast chirp generation. Also, Vadim also mentioned about the antenna. So antenna, AOC, and AIP is always a very interesting discussion point. So from the RFIC and ICC, we have plenty of discussion on the boundary, on the frequency boundary, which is the best separate frequency, and what shall we do for the antennas for the whole system. So Vadim gave a very good example and demonstration of the silicons. Something also already discussed in the previous actually talk is on the millimeter wave, especially the 6G. 6G and sensing and it still have the problems.
I think so. On which slide are you now?
I'm on the slide number 4.
We are still on the slide number 3. Maybe you're sharing the wrong screen. Is it possible?
No,
or
okay.
yeah, maybe you can go into the presentation mode. Or...
Let me redo it and share the whole screen. Okay. Now is it better?
Much better. We are on slide number 4. Perfect. Thank you.
Okay. So now I just share the whole screen to avoid the conflict.
Thank you.
So on the 6G, okay, on the 6G actually 6G, I see the question on the tenders. Why actually on the wireless communication guys is interested on the sensing as well? Because on the 6G, sensing and wireless communication are together. Before the story actually start with narrow beams. For the narrow beams, actually, you want to trace a target. You first have to know where the target is. So that is sensing. You have to use actually the narrow beam first to find the object, then actually focus all your energy to the object, then okay, do the good communication. So in the 6G scenario, sensing and wireless data transfer go together. So they are the same scenario. There is no difference. Whatever, in the sensing and wireless communication, the most important is the phased array and the scanning. And also actually the power is quite critical. So and let's actually also look at the system actually form. System actually, from the system point of view, the system actually, the size of the system, the whole module is scaling. So if we go to the RFIC and ICC from recent years, People are already publishing the whole W-band phase array from the Nokia and LG. The frequency from the 60 gigahertz shifting to the 77. We are now talking about 120, 140, and 220 as well. The whole module size is also shrinked quite a lot. The system level, from the system level, the whole system is quite expanding another direction. Because of phase array, we want actually more channels. Only increasing the channel number can take the maximal benefit from the phase array theory. We can actually focus more energy on the direction, have more detection distance, and we can also actually not increasing noise floor and increase the signal to noise ratio on the receiver side. So on the system level, we are expanding the size of the system, but on another side, on our per channel, we are decreasing, we are scaling, shrinking the per element size. But if we go to the mid with analog signal chain is nearly the same. Here I just draw a very basic architecture of the phase array system. This is actually just a show of the RF phase shifting. But actually, for the phase array system, where you put the phase shifter is very interesting. You can put a phase shifter on the RF signal path, or you can put the phase shifter on the ARO path, or you can put onto the digital domain. Actually, on the history, there are quite a lot of discussion. First, I still remember on the 60 gigahertz, we first working on the RF phase shifting architecture, and we start design RF phase shifter with a reflector type of phase shifter. In that architecture, the loss is quite high. Then later on, we shifted to the switch type of the phase shifter. The definition of the switch type means actually you have actually 4, 5, or 6 stages, and each stage is formed by the filter, and the filter have actually 2 status. The first is pass, then okay, you don't have the phase shifting. If you actually turn the switch on the phase shifting, the filter functional, and it provides some phase shifting. So that architecture is very straightforward, very, very accurate, honestly speaking. But it introduced quite a big loss as well, around 15 dB. So in that year, actually, in the Philips, we also looking into ARO phase shifting as well. But the architecture also related to your system size. How big is your system? Also, actually, that related to your bandwidth, because phase shifting and the delay is quite a similar word, but they are talking about different things. If your signal bandwidth is quite large, then phase shifter is not fit for you. You have to go to the true time delay. So those kind of discussion are always quite interesting in your phase array architecture discussion. Also, actually, in some of the large array like digital large DSA, the analog actually phase shifting, it could be actually quite a benefit to the whole system. So it's always a discussion and always a trade-off on the ADC, on the baseband amplifier, on the RNA, on the mixer. So first, let's look at the low noise amplifier. For decades, actually, the RNA is still the same, didn't change. So this is just a simple example of the 2-stage, actually single-ended low noise amplifier. The topology is quite old, like a textbook, but the most important for the RNA is first is single-ended. Then okay, you have to pay attention to the input noise matching. It's still the same, not changed for decades. Like in the previous presentation, actually, like slot antenna. Okay, in the slot antenna, you still need to have the co-design of your antenna input impedance with amplifier with RNA input impedance, and you can do the differential RNA, but you always need a balloon in front of it to first change a single-ended signal to a differential one. Okay, you can always argue, okay, that is a pseudo differential, but in the millimeter wave frequency domain or in the subterahertz in the D band, the single-ended to differential conversion always actually bring a trouble on your ground signal because you never can have a perfect ground. And you will pay attention to the single-ended to differential conversion and even mode and odd mode. And you would actually design one amplifier. You will design actually two amplifiers instead of one because you have to pay the stability of the differential one and you also pay the stability to the single-ended one. Of course, we have to admit, okay, differential have its advantage on the virtual ground that can get rid of several nasty issue like in the previous talk already mentioned about the ground inductance and in the simulation on the difference on your location of your channels and different location of the channels would introduce different levels of the parasitic and the inductance on the ground and will totally influence your performance. So single-ended amplifier is always a good example to show to you, okay, how strong the impact of the ground inductance could impact the performance of the amplifier. So something we want to introduce in here is actually the interstage matching for always actually is something important for the amplifier design because you have the common source stage, you have a common gate stage, but impedance in between is never actually where compromised in between. You have to find a good partner in between, and those actually interstage matching could be parasitic inductance. It is just allowing you can make a beautiful L shape, beautiful actually rectangle shape, whatever. That is something actually can totally change the performance of the amplifier. Since in the millimeter frequency, the isolation of transistor is not good, those actually impedance could heavily influence your input impedance. So they always actually have to be designed together to achieve a good noise impedance. After the low noise amplifier, on the phase array architecture, phase shift is always the most critical component. Of course, here we will not deep into the temperature effect because like in the previous talk already mentioned about the temperature gradient in the silicon and those actually the temperature variation would introduce the difference of the active component and you would like to put the PDAT close by your transistor or close by your core area. And also actually I noticed on the reference on also mentioned about the Professor John Long's actually the papers on the active component. So how you make the BIOS is also critical because you have the voltage BIOS, you have current BIOS, and how you want to make the BIOS and how you want to make the temperature stable is also critical. But here in my part, I want to mention, okay, besides active component, the quarter generator is also crucial because you can actually draw there's mathematical equations you can roughly calculate for you actually phase shift accuracy how much of the phase mismatch you have to achieve for your input quarter generator. That is tough. Also that mismatch is go together with your bandwidth. You cannot talk about phase mismatch without talking about the bandwidth. That's unfair. So here I take the 60 gigahertz as an example because 60 gigahertz, you have 7 gigahertz bandwidth. That means nearly close to the 10%, more than 10% of bandwidth. That's very wide band. So in that part, in that frequency, actually, since as we discussed on the previous slides, the low noise amplifier is single-ended. So the quarter generator, you would prefer to have a first single-ended to differential converter, and then you have a differential I and differential Q. So you can imagine, okay, how mass the ground and how mass the phase is. So the well-defined of the ground and well-defined of your signal path is quite crucial to achieve the phase. And also there is also a trade-off on your Q, on the quality factor, because in one side you want actually good quality factor because you don't want high loss, right? And on the other side, you would prefer to have a large bandwidth. So you have a compromise about the quality factor of the passive component. And something we also have to discuss, to consider is on the terminator, the impedance of the terminator. Because on the on the quarter generator, if we don't discuss the impedance of the terminator, it's also unfair because that terminator can influence your bandwidth quite a lot. So that's a lot of discussion point on the quarter generator for a phase shifter. Especially nowadays, we use a active IQ vector phase shifter quite a lot. So from the measurement, you also see that the phase shifter, because if you see the input of the phase shifter, you don't want actually the phase shifter to have a very big variation. That's crucial because on the signal chain, you prefer actually that each stage have a good reference plan. So that reference plan means, okay, less reflector. But if on the phase shifter, if you change your VGA on the I parts or on the Q parts, that means your input impedance definitely will be influenced by the VGA, and you will see a big variation on your S11 and also on the S22. So from my point of view, not just the phase shifter cannot just evaluate the phase shifting capability and RMS error of the phase and RMS error of the gain. Also have to look at how good is your input S11, because that can actually make your whole design nightmare. After the phase shifter on the TX part, the most crucial part is the power amplifier for sure, because we need to generate power. And for the power amplifier, the most interesting thing is actually the power combining. This actually the power amplifier we designed with output power around 20 dBm. I mean on chip 20 dBm, not EIRP. So you have to actually, after the back of envelope calculation, roughly we need to have actually 4 sub-PAs. But actually combining them together is a very interesting thing, because you have roughly, you can have actually 2 ways of the combining. One is actually series combining, another is parallel combining. So you either combine in the current domain or you combine in the voltage domain. So what is the difference between them? That's always a discussion point in history. So from my point of view, it's just the impedance, because everything actually on the millimeter and the sub-terahertz is on the impedance. If we look at the mathematics tells us, okay, the series combiner, you will see the M and N on the M and N actually will reduce your load impedance quite a lot. So that means you can have optimize the impedance small. While on the parallel combining, you will have the different expression, and you can have one more variable of the N compared with series combining. So you can tune the impedance in another way. So from our actually experience, and we do the both series and parallel in history, and we find out, okay, we can do first to do the we do the series and parallel in combination. That's a very good actually practical way. So in that case, actually, we at the 70 around the 77 gigahertz, we can generate output power more than actually 20 around actually 20 dBm, close to the 90 19.7 or 8 dBm output power. So as I mentioned before, okay, the VGA on the phase shifter is critical. Also, the VGA itself on the signal chain it is very critical. Why I meant, as I explained before, the reason why it's critical because you cannot change the input impedance quite a lot on the signal chain. So if we look at the topology of the VGA, you can name actually the gate bias control type of VGA or current steering type of VGA, or some people also use attenuator to do the VGA. Okay, so if we do the fair comparison and list them into the digital assisted, the return loss or input 1 dB compression point noise figure. Yeah, digital assisted, that means, okay, you can put a DAC, a DAC to achieve the control voltage from the digital to the analog domain. Both gate bias and current steering can do that kind of the conversion. Also, attenuator type also can do it. But if we look at the return loss, input S11 or input S22, the current steering type of the VGA have one very unique property. Okay, input impedance is quite relatively stable because you only actually you pay for the current. You pay actually extra current path to feed the current into your GM transistor, while your M2 transistor, your common gate basically didn't change. So that actually help you to stable the input impedance. So we take an example, we just take an example of that type of the current steering type of VGA. And from our measurement S11, you can see, okay, the input variation is not so big. It is quite small actually. And the tuning range is also okay. It can achieve the tuning range roughly in the range of the 7 dB. So it can meet the requirement of the VGA on the signal chain and of the VGA on a 60-bit phase shifter. So if we line up all the mid-wave signal chain, because in the 5G we do the project for the car radar and for the 5G, so we have the chance to line them up. So here I just show one example of the one single channel to line them up with a PA, VGA, and the phase shifter. No, this one not with the phase shifter. And okay, with from the 22.3 to the from the 42.3 to the 48.4 gigahertz. Okay, we can achieve a 64 quant actually data transfer. It's quite it's a good experience. So if we finish all the block, then next, okay, definitely we want to do the beautiful beamformer. This is our first actually example today. It's my first example today to give on the beamformer. This is for the 5G. Actually, this is not just for the 5G. It covers the frequency from the 30 gigahertz directly to 40 gigahertz. And it including the it included the receiver channel and the transmitter channel. The TX part actually, we have actually on-chip sub PA to change the power level. Actually, I prefer to have the small PA instead of one big PA. because in that case, actually, you can have a very control of the efficiency. Because if on the TX part, efficiency is very critical. As I mentioned before, okay, the phase shifter, but this phase shifter on this version, this work we published in the Asia Solo State years ago. And this version of the phase shifter, we have the digital controlled phase shifter. The digital control means, okay, on the common gate CG topology, on the CS CG topology, in the parallel of the CG, we have actually quite a lot of the transistors in parallel, and we can turn on and turn off the common gate to actually to tune the gain of the VGA. In this way, we can tune the phase of the in the RX or in the TX. Actually, something we learned in this project is actually the interstage matching is quite critical, because we are talking about a TRX on the 30 to 40 gigahertz. That is interstage matching and load condition, both dominant a broadband front end performance, honestly speaking. So this is actually our 4-channel beamformer. And for the isolation consideration point of view, actually we put the TX on the edge of on the silicon, and we put the RX on the middle of the silicon. So in this way, we want to actually separate the TX as far as possible. And from the measurement, it shows that it can achieve 5.6 degree, I mean the scanning angle. And also it can achieve very high accurate phase shifting capability. Next, I want to show is a W-band beamformer. This is actually a 16-channel, 70 gigahertz receiver. The frequency is way higher than previous 60 gigahertz design and 30 to 40 gigahertz at 5G beamformer. This actually the 90 gigahertz receiver, but look at the topology, it's nearly the same. You even cannot tell what's the difference between the symbol. Yes, if we just draw everything in the point in the same symbol. But the design philosophy is a bit different, because in this such a high frequency, how you achieve the phase shift is quite critical. Because something we don't like or something we, as frequency go higher, we have to face is active component provide less gain. That's actually, I still remember from Vadim's actually the presentation, he gave a good actually technology trend on the CGE and the CMOS. The Fmax of the CMOS on the 40 and the 22 technology node, the Fmax is around 300 gigahertz. So that means if you design an amplifier on close to the 100 gigahertz, your gain is quite low. Per stage can contribute roughly 6 dB. But from the as a receiver, as a first block of the receiver, your low noise amplifier have to actually at least provide 15 dB gain. So that means, okay, you have to stack quite multi-stage amplifier together to form the low noise amplifier. And in the same time, we all know, okay, the noise cannot be benefit from multi-stage, because the first stage dominant the noise. If your gain is not high, then your second stage definitely will contribute your noise. If your first and second stage in together cannot achieve more than 10 dB, that means your third stage also will contribute quite a lot of noise. So in this project, something quite suffered is actually the limited gain from the amplifier actually totally make the VGA not easy to design, and RNA also, and the phase shifter. So in this actually the W-band 16-channel receiver, we use actually 5-bit octant selector and reflect type of the phase shifter to achieve actually 360-degree phase shifting. Also, we use actually the VGA phase shifter VGA. Yes, we go back to the very traditional VGA phase shifter VGA topology, this sequence, to make sure actually when you tune the gain and when you tune the phase, the signal actually at the interface between the LNA and the power combiner, the reflect the at those reference plane, the signal actually is quite still quite stable. The the reflection is less. This is actually in the measurement in the small chamber, and we can achieve -30 to the 30-degree actually the scanning capability with our beautiful silicon. This is we measured at 94 gigahertz with actually these 16 channels, of course. So next is the 77 gigahertz car radar. Yeah, this is the work we used to present in the ICC 4 years ago, roughly. 70 gigahertz car radar is actually as in the previous actually first presentation, a second presentation, third presentation, we all actually mentioned about the 77 gigahertz is quite hot market, but we also point out the cost is important. And from previous, Vadim's talk is also mentioned about the antenna is a quite critical part. I totally agree with you. So that's why we use actually, we put the antenna on the package, and we also considering the silicon area. We use actually in one package, we have actually put two dies in the master and slave mode to save actually the silicon area, not have very big die. And also in this way to separate in the two part, we can actually have less, we have less thermal effect. This is architecture of the actually our MIMO antenna array in the package. It include the 4 channel for the receiver. For each die, we have actually 4 receiver channels and also 3 sub PAs on the die. And we put the power combining on the antenna. That's a multi-feed antenna. Actually, it's the same philosophy like 2-feed slot antenna. We want to actually to save the power combiner. We want to shift the power combining actually the function to the antenna part. In this way, we can save one component on the die, not just save the area, also actually reduce the loss. On the chip, of course, there are temperature sensor to control the temperature to make sure the PTAT for the transistor BIOS is transistor BIOS is okay, and also on chip LDO to make sure the stability of the BIOS. Because a lot of actually the trouble things is from the BIOS line and from the supply line. So you have to actually to consider that. Also, I totally agree with previous actually talk mentioned about low omega ground path. That's also very critical for the complex system. It's not just like a one die. Okay, you can have a I/O pad very close to your BIOS, or you can have a very symmetric layout on your actual test chip. As a complex system, you will see actually the different power domain will be coupled to each other. The couple can from the sky, I mean the power, or can couple from the ground. So a lot of the very interesting discussion on that as well. But I do enjoy previous presentation because he give quite a good discussion. So we use a 3-feed antenna in package to actually to increase efficiency, and we have the 3 sub PA on the die to tune the power level. Very effective ways from our measurement. Also, actually, on the PCB on the laminator, we have the reflector. the reflector actually is designed, of course, the reflector have to design together with the silicon itself, because the thickness of the die and the reflector, and because this is those are actually in the field of the metal material that field, because you want a reflector signal in phase with you actually with the wave you want to transmit. So reflector have to be designed in a good way to enhance the wave instead of the absorber. Because I remember in the first presentation today, the Bosch provide a good radar board. On the radar board, they have actually the metal material as absorber. So for the reflector design, it's another way. You cannot design into absorber. You have to be designed as a reflector to enhance the signal. So that's a very critical part. And also the feeding line, because as defined by the God, okay, the line, the PA on the left and on the right and on the middle, definitely they have a different paths to the antenna. So, but those signals have to be arriving the antenna in the same phase. So you are going to definitely, for sure, as we show in the presentation, you will put a small twist line on the middle, on your button, on your top, to make sure, okay, they are totally in phase. And also something very interesting is on your impedance, because as a co-design part of the PA and on the feeding line on the patch antenna, the impedance transfer is critical, because you want to start from the low impedance to a high impedance, or you start from the middle impedance to somehow a little bit high impedance, because as a loading for a PA is always a loading for the antenna. So when the PA is on and off, the impedance is totally different for the antenna. So you have to make them all happy, as actually Vadim explained in the on-chip slot antenna, the 2-feet slot antenna is the same theory. You have to be totally balanced the impedance of the PA and the antenna. So in the measurement, okay, very lucky. Our radar can do the measurement, can receive the signal, can transfer a signal, and also can test well. So today, actually, in my presentation, I talk about bandwidth quite important for sensing and communication, and in the 6G, sensing and communication is merged, and innovation always the first thing first. So finally, I have to thank all my teams and all my actually previous colleagues in the company, and my friends in the university, in the worldwide university. Thank you for listening.
Thank you very, very much. How was excellent talk. Very informative. Maybe a very short question if anybody has in the chat.
Yeah.
If not, maybe the best would be to put the questions into the Q&A, so you have more time to answer the questions. So thank you very much, and I suggest we go then to our